INSEE is a proud member of the Siam City Cement Group Public Limited, a leading cement manufacturer in Southeast Asia. The Siam City Cement Group provides world-class construction materials to a host of countries around the world. This includes Cambodia, Bangladesh, Vietnam, Thailand, Indonesia and Sri Lanka. With a plethora of landmarks and buildings that define the skylines of these countries, the Siam Cement Group pledges to be a role model in corporate governance and sustainable development. INSEE Cement, Sri Lanka's premier cement manufacturer, is the brand behind our country's leading cement products and the driving force behind making Sri Lanka more sustainable. With a reputation built on outstanding performance in the quality of our products, unparalleled customer service, the dedication of our employees, our respect for the communities in which we operate, and our ambition to set the standards for the industry of tomorrow, we have contributed to the growth of Sri Lanka with iconic developments across the island. Just to name a few: the Lotus Tower, Altair Residencies, the Colombo South Harbour, Southern Expressway, Mattala Airport, the Kalladi Bridge, the Kotalavala Defence University, Mahinda Rajapaksha International Cricket Stadium. INSEE has cemented its position as the most preferred local manufacturer of cement in Sri Lanka, with its widespread distribution network comprised of over 7,000 dealers in retail segment located island-wide. Today, we have 2 plants in Puttalam and Galle and 2 terminals in Galle and Colombo. INSEE's Sunstar brand is Sri Lanka's first cement product to be awarded the Green Labelling certification by the Green Building Council and was the first blended cement to launch in Sri Lanka. INSEE has a wide portfolio of cements and services to suit all your construction needs. The most popular among them, INSEE Sunstar, INSEE Mahavali Marine Plus, INSEE Extra for mass pouring concrete, INSEE Rapid Flow Plus, INSEE EcoCycle, INSEE Concrete, Conwood by INSEE, state-of-the-art innovation and development facility. Having been a part of Sri Lanka for almost a decade, we will continue to build on our long heritage of shared loyalty, creating trusting relationships with our business partners, people and community, and delivering our promise of building the nation.
And today's session, as Dishan said, that it is about the new SLS 1697 Portland composite cement. And the third thing is that today Switzerland is playing the quarter-final against Spain, such a small country. Thanks to discipline, thanks to motivation, they could do it. Therefore, that is exactly the same when it comes to innovation. Therefore, when we have the right ingredient, as in Sri Lanka, impossible is nothing for us. Huh? Therefore, that is why I'm really grateful to have this opportunity to present you the new SLS standard on Portland composite cement. Host is a big part of the screen. Could you please let me have share my screen, Gayani? Okay. Therefore, the topic today, as we said, is about the new SLS 1697, the Portland composite cement for sustainable performing concrete. Before really introducing the topic, I would like to somehow go through the motivation why we have been working with the working committee to develop such a standard for Sri Lanka. Of course, I would like to discuss about 2 main challenges to cope with the society increasing need for construction materials. What it is really for us exactly, and how this has really somehow is going to put a lot of pressure on the way we in Sri Lanka we have to stay competitive. After that, I will introduce the new standards with future advantage benefit of it, and will present as this cement has been used for decades in other countries. I would like to also present you some example of international projects where Portland composite cement has been used. And I will end up with the INSEE innovation collaboration space, because this is like the natural path We have started when we talk about collaboration, because this is very important. We want to move really from this circular mindset in order that we can collaborate together, and that is really one of somehow key platform we have to invite all the stakeholders to join us and to collaborate to develop a sustainable performing solution for Sri Lanka. Therefore, just to start, I would like to start first with the first challenge. In theory, what really matters for us when we look the global population growth, and we look to the cement demand constantly increase, even though we went through the different crises the last 50 years. We still see high demand in cement volume, and this go really very linear with the population growth. Therefore, we expect in 2050 to reach almost 9 billion inhabitants. And when we look to that, it means that we need to build more school, more houses. We need to build more infrastructure. We need to develop. That is really important because we cannot stop. We have to develop. And as you know, today, concrete is the choice number one for engineers, thanks to its versatility, to its performance, to its cost somehow benefit. Concrete is somehow the construction material the most used. But also concrete is produced with a wonderful product called cement. Now, when we look to the cement demand, if you look, for example, 2017, we have been using the planet worldwide around 4 billion tons. 4 billion tons of cement, and these 4 billion tons somehow represent, if we look where they have been produced more than 70% in our region in Asia. Therefore, that is something important to keep in mind, because very often some company will I say start to produce cement where there is less restriction, environmentally restriction. But today we will see that there is a huge pressure in terms of carbon footprint. I will come back to that. And also when we look to the concrete, world concrete production, 2017, around 7 billion. Sri Lanka is around 12 million cubic meters. This is what we have poured last year in Sri Lanka. Therefore, there is really quite intensive use of cement, of concrete to sustain the development of every country in this planet, including Sri Lanka. Therefore, when we look to that, it is also important to mention here that cement is the third largest CO2 emitter after fossil fuel and land use. Somehow, what is important, what you can see here, that the cement industry alone contribute to almost 8% of the global CO2 emission and climate change. This is really tremendous. And when we look to the embedded carbon of building products and construction, they are responsible for 11% of the global greenhouse gas emission, and 20% for global building sector emission. Therefore, the footprint is quite impressive when we look to the footprint in terms of climate change. And eliminating this emission is key to addressing the climate change and meeting the Paris Climate Agreement target that Sri Lanka has signed. Therefore, this is one thing is about the footprint. As you know, every equivalent to every ton of OPC, we are emitting around 0.8 to 1 ton of CO2. Therefore, the footprint is quite high. But what is also important to mention here, that the embedded CO2, okay, when we look to compare to operational carbon emission, okay, the embedded carbon CO2 is very important here. Okay, therefore we have to address this, because this is locked in place as soon as a building is built. Therefore, when we talk about operational carbon, you know, we see today a solution in terms of during the use phase of a building, that we use more somehow green energy, like non-fossil energy, electric coming from solar, from wind. Therefore, there is a lot of somehow improvement there. And but when it comes to embedded CO2, it is very important that we look to the product as it is during production, and mainly the cement. Okay, and that is why if you look here, if we do not achieve the 65%, I would say, reduction in total global emission by 2030, we will have lost the opportunity to meet the 1.5 to 2 degree threshold and climate change. That will be irreversible. Therefore, we have to really look. That is why if you look, most of the big cement player companies, even though in our region, they have already committed in terms of for 2030 and 2050 roadmap with their CO2 reduction. Therefore, we need to have immediate focus on this embedded carbon reduction. Therefore, how to do this is through circular economy and innovative greener products. Therefore, we move totally out of the linear to the circular economy and look after any, I say, byproduct and integrate it to solution development. The carbon capture and usage. Okay, we talk about carbon sequestration, carbon capture, and also alternative to fossil fuel. For example, during when we produce in Portland, we use alternative fuel, but also we can use, I say, solar energy. We can use wind energy to really reduce the footprint. There are solutions, but the most somehow effective one is to reduce the clinker factor of the product, because the clinker emit really more than 60% of the total CO2 when it comes per ton of cement. Therefore, that is really important that we look at it. Now, in practice, what happened? That the carbon price, if you look here, the carbon price development since 2018, according to the European trading system, you see that we can be facing very soon, especially in Sri Lanka, we are importing. We are importing only in Portland. We are producing around 1 million tons, but we have to import as a cement industry in Sri Lanka around, let's say, 4-5 million tons of clinker. Therefore, imagine that suddenly we have to pay 20 to 30 US dollars per ton. Therefore, that is something that we just cannot afford. That is why we need to prepare. Okay, we have a good roadmap. We need to prepare ourselves in order to stay competitive and try as much as possible to develop solution technology, even proven technology where it has been used other place, and try to somehow bring it to Sri Lanka. That is very important, even though it is a good incentive also for the Lanka cement producer, because it's a good incentive for them to invest, therefore develop innovation, and therefore develop the next generation to take over these challenges and turn it to opportunity for Sri Lanka, as several countries have already started. Now, the second challenge I would say that really matter to us in theory is the trend toward urbanization. Okay, we say population growth. Okay, population growth, we need to build more, but when you talk about urbanization and mega cities, we build differently. We are not building only in a horizontal way, but we go vertical, we go even underground today. Okay, therefore, technique of construction, the engineering properties, even though exposure conditions are changing, because we are getting more close to coastal area. People develop more, especially when you take an island. We need to be close to the sea. Okay, therefore, this has also another impact, because we have also to consider the new engineering property that is requested to assure that we build in a sustainable way. Okay, and for example, if I look when we tall building, you know, we say vertically. If I look, for example, if you look the last 50 years, when I look tall buildings, I mean, more than 95%, they were built in North America. Today, more than 70%, 70% to even 80% of the world's tallest 100 tallest buildings are in emerging countries. And emerging countries mean Asia, Middle East countries. This is why we built really very much somehow vertically. Therefore, this is again, it has an impact for us. It has an impact in terms of also technique, solution development to assure that we can fulfill engineering properties. Okay, for example, when we talk about e-modules for tall building, okay, when we talk about durability for infrastructure that need to be built now over 50 years to 100 years, therefore, these aspects are not linked to the compressive strength. There are other properties, and that is why I would say this, in fact, will have an impact. Just as an example, this is something I got from Dr. Tushara. If you look Shanghai, just to see the reality of that, Shanghai 30 years back, it was like that. And Shanghai today is like that. Therefore, this is not Shanghai. If you look Port City project in Sri Lanka, Port City development project, it looks like now with all the reclamation done, okay, and it will look like this in 30 years. And what you see here in front of you, this is like you are building in Colombo, Singapore, equivalent to Singapore. Therefore, you see the implication for a country like Sri Lanka when we are an island. Therefore, we are really somehow challenged by supply chain, by raw material. Therefore, we cannot miss any opportunity to assure that we can build in a sustainable way. When I say in a sustainable way, we build with very low social cost. Okay, that is important. When I say very low social cost, because we talk a lot about that concrete is the universal construction material, but also a possible universal construction problem. You have been all listening to the news. We don't want that this happen to us. The Morandi bridge in Genoa, in Italy, 2018, 2020, again, another bridge in Italy. I don't want to show the picture from the last collapsing of the building that is facing the Atlantic Sea in Miami. Okay, because they did not finish to somehow investigate it. Therefore, respect to the family who are there, I decided not to show this picture. But here again, if we build and we do not consider other parameters than the compressive strength that are directly linked to the exposure condition, something could turn not to our benefit. That is why I would say it is very important that we look to that. Okay, and there are opportunities, there are solutions for that, and this is what I would like to share the next 45. Therefore, we need to move from this prescriptive way of building, where we have the mixed design is the most important. Mixed design, we cannot change mixed design. After that, the compressive strength. Everything is based on the compressive strength. If we comply, it is accepted, we build. If you have a problem, we have to repair, and this is somehow high social cost. Okay, but we know also that the last, I say, decades, okay, when we look infrastructure project, a very strategic project, they have been built to last over 120 years, okay, using durability indicators and with composite cement. None of them with the OPC. Therefore, there are a good reason. There are very good reasons, because those bridges, what you see in front of you, are not designed considering only the compressive strength. Okay, they are using what we call performance-based design, where the compressive strength and an indicator could be the porosity, could be the chloride, could be the sulfate, could be the heat, okay, is integrated in the service life model, okay, to get compliance, to check, and to go for construction. Okay, that is when we come to sustainable performing concrete and we talk about this composite cement, superior blended cement. That is the main reason why they have been used successfully, okay, with proven technology. Therefore, it's really time that we push on the bottom. When I say to push on the innovation bottom, okay, is really there are solutions. Sri Lanka has not only the capability, but Sri Lanka also has today the project that need this bottom pushing on the innovation. Therefore, we have to look after products that are sustainable, emitting less CO2, less damage on the climate change, that will offer extended service life, with very reduced maintenance costs, economically viable. We cannot afford to pass high costs to end user. Imagine today, tomorrow, if you have to increase the bag of cement per, let's say, 100 rupees, this cannot be. Okay, and also to support the overall commitment to sustainable development, not only as a cement industry, but to support the country, to support Sri Lanka to really fulfill its commitment towards sustainable development, especially the Paris Agreement. Now, I come back now to this is just to introduce the topic. What is the motivation? The motivation, you can see it now, is I'm talking here mainly on two aspects on the motivation. One aspect is the global climate change impact due to CO2. Population is growing. We are in an island, therefore scarcity, we need to be independent, therefore we need to develop solutions, therefore we need right standards, okay, to let us push on the bottom for innovation. Okay, that is really why I want to come to this new Sri Lankan standards, the SLS 1697, the Portland composite cement. And you see Portland, because all the green products, they are all, their legacy, their ancestor is OPC. Of course, they are all Portland based. Okay, now, just to start, okay, to give a little bit the framework of the standards, these standards has been approved by the sectorial committee on building and construction on the 24th of February. Therefore, today the cement producer, okay, they can produce such a product and sell it in the market in Sri Lanka. Second, this standard has been prepared to enable the manufacturer to produce the Portland composite cement equivalent to OPC Portland cement on the basis of compressive strength at 728 days. Therefore, as you know, in Sri Lanka, we have the 32.5, 42.5, but we are producing, or the cement industry is offering the 42.5, either N or R. Okay, therefore, this SLS 1697 will be equivalent to this compressive strength for OPC. Last but not least, when this was prepared, this new standard, we got assistance derived from the publication of international standard, mainly the BSEN 197. Okay, therefore we gratefully acknowledge, and for that I would like just to somehow to show you where this standard is coming from. And for that, we have been forming a working committee, and the working committee, it is great, as you can see, it is from academia, from the private, from the public sectors, from with SLSI. Therefore, it was the chairman of this working committee group was Professor Anura Nanayakara from University of Moratuwa. I mean, well-known, I say, opinion leader, academician in Sri Lanka. Dr. Tushara from Open University of Sri Lanka. He will be sharing today the discussion. He will join for the panel discussion. Miss Dr. Patirana from University of Peradeniya, and Dr. Harsha from University of Pune. Also, we have a member from institution, consultancy, organization, corporation, association, okay, who were also sitting in this working committee member, plus SLSI, and the Lanka cement manufacturer is mean Siam City Cement and Tokyo, okay, and Tokyo Cement. Therefore, this was the working committee, and also from the secretarial committee member, okay, for cement and construction expertise, we have Professor Ranjit Desanayake. He is a senior lecturer at University of Peradeniya. Therefore, he is also today present for the panel discussion. Thank you so much. And also Engineer Magala De Silva, who is SLSI board member from Synergo Consulting. Thank you, Engineer Magala. Also, he is going to also participate to this panel discussion after my presentation. Therefore, this is really something great, what I'm saying here, because you see that this is really like the Swiss team. It's like the Swiss team. It's a winning team because it represents all stakeholders, from the construction, from the private, from the public, from the consumer, from the academia, that this standard has been developed. And I think that is really a great, I say, achievement. Now, when it comes to composition and notation, I just want to somehow go very fast. Summary, probably you know our standards in Sri Lanka, but just to make a kind of refreshment. You know, as you know, we have the British standard, the EN197, with 27 products, okay, what we call common product, and you have also 7 products. These are what we call sulfate-resistant common cement, okay? Now, if we look at the 3 standards we have today in Sri Lanka, okay, we have the SLS 107. This is the same one according to the EN197, okay, the OPC. After that, we have the SLS 1247. This is blended hydraulic cement. This is also fully coming from the BSEN 197. After we have the Portland limestone cement, the SLS 1253 also, it is derived from the BSEN 197. And now we have this new standard, the SLS 1697, the Portland composite cement. Therefore, you see, this is a cement that we just took out of a box from this BSEN 197 because it was time for Sri Lanka to move toward a solution that, as I said, could really help the industry to turn these challenges, what I have explained at the very beginning, as a motivation for us to opportunity. And therefore, as you see, this is not a development that we have done in Sri Lanka. It has several decades of proven technology application that I will share with you at the end of the presentation. Now, if I come to the composition, you know, for example, the OPC, where the main constituent is only one, is clinker. Okay, therefore, in OPC, we have clinker, and we have what we call a minor addition, 0 to 5%. Okay, now, when we come to the, for example, the 1253, the Portland limestone cement, here you don't have one constituent, but you have 2 main constituents, clinker and high-grade calcium carbonate, what we call limestone, the LL class. This is a high grade. Also, you have here the minor addition constituent, 0 to 5%. Now, this is now we have 2 constituents. Okay, now when we come to the SLS 1247, here you have also 2 constituents. You have 2 main constituents. But the 2 main constituents are clinker, and either you use pozzolana natural or calcine, or you use granulated blast furnace slag, what we call slag, in Sri Lanka, or fly ash, either silicium or silicious of calcareous, but in Sri Lanka, we mainly use silicium. Okay, therefore, and these 2 main constituents is you have to mix clinker with one of them. Therefore, either I use clinker and natural pozzolana, or clinker and natural calcine, or clinker and slag, or clinker and fly ash. For example, if I look to the product of Holcim, of INSE, sorry, therefore the OPC will be the RF, the Portland limestone cement will be the Sansta. If I take a slag base, will be RF plus or marine plus. Okay, the same, that is slag base, or we have also, we are producing in Putlam the F class, the extra or the marine plus or the alpha, this is flash base. Therefore, the 2 main constituents is clinker with one of these additions. But now, when you come to the new SLS 1697 Portland composite cement, you see the constituents are exactly the same. We have the clinker, we have the pozzolana, either natural or calcine, we have the slag, the fly ash, either silicious or calcareous, and the limestone. Therefore, all constituents that are in the OPC, in the Portland limestone cement, in the blended hydraulic cement, are exactly the same in the Portland composite cement. But the difference here is we have a multiple main constituent. Therefore, in the Portland composite cement, the producer has the possibility to mix different additions. Therefore, I can mix, for example, pozzolana and slag and limestone, or fly ash and limestone, or limestone and slag. Therefore, I can mix with 2 variants. The what we call PCCA, M mean mix, or PCCB. The A mean 12 to 20%, and the PCCB between 21 to 35. The only difference for the A is when I look to the blended hydraulic cement or when I look to the Portland limestone cement, here we start at, if you look, I go back, you start at 6 to 20. But for the Portland composite cement, you start at 12. And you have always this minor addition, 0 to 5%. Therefore, in terms of constituent, there is not something that we bring that we have never used in Sri Lanka. Okay, therefore, the constituents of Portland composite cement are exactly the same constituent, but just in the Portland composite cement, you have a multiple main constituents. This is just the difference. Okay, now I have talked about how to mitigate the CO2. How to mitigate CO2? I mentioned the clinker factor. Clinker factor is really important here. Now, when I look, for example, the first year of publication of all these standards, if I take, for example, the OPC, it was published first time in 1971, where we know the carbon footprint is around 1 ton per CO2. Okay. After that, it took almost 30 years before the blended cement, either Portland limestone cement or blended hydraulic cement, came to the somehow we got this standard in 2003. Okay, therefore we had here 30 years where our engineers, our project, all the experience was built on the OPC. But you agree with me, during that period, a blended hydraulic cement, Portland limestone cement, Portland composite cement, they were all already developed and implemented in several countries. And that is what I will show you. Now, when it comes to the footprint, the Portland limestone cement, we can reduce the clinker up to 20%. Okay, therefore CO2 can be reduced to 20%. After that, when I take the blended hydraulic cement and the new Portland composite cement, I can reduce up to 35% the clinker. Therefore, I can reduce the CO2 footprint up to 35%. And this becomes very significant. Now, the difference between them, as I said, if I take the Portland limestone cement and the blended hydraulic cement, I have only one type of mineral addition. Other limestone, or here slag or fly ash or pozzolan. Okay. Now, with the new Portland composite cement, it's a multiple blend. Therefore, that is good. I would say I put a count. Is good because this let us push on the bottom of the innovation and look for opportunity. Okay. For example, on the pipeline today, if I look our R&D activity, we are investigating on a new aluminosilicate material in Sri Lanka. Okay, to develop them and start to produce cement based on them. Therefore, we'll be, let's say, improving our let's say import footprint. Let's put it like that. Okay, and that is good. That is a good incentive, and this is the best way that we also somehow grow our capability. Okay, and continuously develop ourselves to be ready for any new innovation that could be implemented in Sri Lanka. Now, here I would like to start to talk a little bit more in deep when it comes to the Portland composite cement production. It has what I call a complex mineral system. What is this complex mineral system? This complex mineral system is that, when I look to all the ingredients that are used today in our 4 cement standards, they are all within this ternary chemical, okay, composition of calcium, silicate, and aluminate. Okay, therefore you see you have clinker, you have slag on the left side. This is why we say slag is a latent hydraulic, because slag, it has a basicity 1 and more than 1. Therefore, slag by itself, it can react with water. Okay. However, when I take, for example, natural pozzolan, fly ash, or silica fume, they are different. These are what you call aluminosilicate material, that they need an activator. They need the lime from the hydration of the clinker to activate them. This is not like slag. Therefore, you see, this is complex because not every slag is slag. Not every clinker, is clinker. Clinker depends very, very much to the raw material you are using to produce the clinker. It depends very much to the process you are using. Okay, it's the same for the slag. Okay, the slag is a byproduct, not from the steel industry, because the steel use the iron cast that is produced to produce the steel. Okay, therefore there is a byproduct called slag. Okay, fly ash, is coming from power electrical generation plant. Therefore, like in Norochili, this is where we get our fly ash. You can have also pozzolana, either they are sedimentary or volcanic based. Silica fume, not often used in Sri Lanka. And you have what we call the clay, the calcine clay, not still in Sri Lanka. Therefore, if we look to this ternary system, calcium silicoaluminate, we are saying it is complex, but of course, a cement producer who has a kiln, for example, like INSE in Putlam, we have a certain what we call cement expert tools design. Therefore, we have our what we call intrinsic indicators to combine depending to the intrinsic chemical composition of this aluminosilicate phase, to develop this Portland composite cement. That is really important. In cement chemistry, if you do a cement hydration course, you will see how relevant is it. Now, this is when it is used now. What we call the INSE Smart Axe complex organomineral. Okay, it has a combination of what you call a triple reaction. I will come back to this triple reaction because it's very important, and I will somehow explain you why this minor addition, the 0 to 5%, is changing now the possibility for Portland composite cement to reach higher strengths. I will explain that. Therefore, thanks to the fact it's a multiple constituent, we don't have only one or two constituents, but we have a multiple constituent. Therefore, in this ternary system or quaternary system, okay, we can optimize the particle size distribution. Therefore, of course, this will be very difficult if I call our company in Thailand and tell them, please send me your composite cement. This is difficult. But if I do it, we do it ourselves in Sri Lanka, we can do it. Therefore, we can optimize the particle size distribution. That is very important because the grindability of clinker, of slag, of fly ash, of limestone, they are different. Okay, therefore, this will give us this opportunity to optimize the packing density. And at the same time, if we combine the chemical part to the physical part, we are able to have a very strong, what we call the physico-chemical synergy. I will explain it later. That is important because when you move from a normal concrete to high performance concrete, as I said, is not only about the compressive strength, because the compressive strength, you achieve it if you look after the water cement ratio to a certain extent. But if you look after the porosity of concrete, you can have two concrete with the same compressive strength, but one has a higher permeability than the other one. And that is exactly what I'm talking here about, the triple reaction. How this triple reaction with Portland composite cement, and that is the main reason why if you look bridges, if you look big infrastructure worldwide, okay, buildings, they all use this type of Portland composite cement. Okay, that is really the main reason. Now, let's look after the hydration. Some of you, you know some of my slides, because now I will dig a little bit more when it comes to the Portland composite cement. Now, let's have a look to the hydration reaction. If I take, for example, the SLS 107. This SLS 107, as I said, is one constituent is clinker. You have minor addition below 5%. Of course, all cement, you regulate them with gypsum, okay? Therefore, mainly is clinker. That will react here. Therefore, the clinker, if you add water, you have hydration reaction. You form two main products. The first one is what you call calcium silicate hydrate, and the second one is the portlandite or calcium hydride. That is the same. Let's call it portlandite. Now, as an engineer, I'm not a chemical guy, I'm an engineer, I'm a civil engineer. Therefore, for me, what is important to me? What is important for me to know that whenever I good performance, this is thanks to the calcium silicate hydrate. Every time I have strength, I have durability, this is thanks to the calcium silicate hydrate. Now, whenever I have weakness, I have issue. This is coming from the Portlandite. Okay, because this is a soluble salt. If you dissolve it, you can carbonate it, you can have acidic attack. I will explain it later. That is why it is really important that when you use this, why if you look, for example, in the past, mixed design sometimes rich in cement just because they need to assure that they have developed enough CSH. That is the main reason. Therefore, when I look to this SLS 107, you have one reaction, and this reaction will produce a very good product called calcium silicate hydrate, as you can see in the microscopic picture here from the scanning electron microscope, and Portlandite. You see already in terms of size, how the Portlandite is very big crystal, salt crystal, very soluble compared to the CSH are more at a nano size. Okay, at the nano size. Therefore, that shows already here that there is a big gap. Like in concrete, you have a big gap. When you look constituent of concrete, the smallest one, cement, you say 20 micron. If I take the coarse aggregate, is 20,000 micron. You agree with me? From 20 micron to 20,000 micron. How I will mix this to keep a certain cohesiveness. This is why packing, okay, maximum packing, development of hydrated product are important. Otherwise, you can lose the cohesiveness. Have some issue in fresh or hardened concrete properties. Therefore, now when I come, for example, to the blended hydraulic cement, the 1247, the same I have clinker. Therefore, if I mix this cement with water, I will get the same reaction, okay, with calcium silicate hydrate and Portlandite. One will give me strength, and one will give me the problem, the what I call the challenge. Okay, now, of course, in this cement, I have the aluminosilicate material, like fly ash, like pozzolana, like slag. Therefore, you have SiO2. This SiO2 will combine the calcium, and therefore you have a second reaction called pozzolanic reaction. And this pozzolanic reaction will turn the Portlandite, that is the weakness in the concrete when it comes to durability, to strength. And suddenly you are mitigating the problem with Portlandite. If you go and you ask Port City why they go exclusively with fly ash cement in say extra, that is the reason. I will explain you later. Okay, that is the main reason. Therefore, it's not about megapascal. It's about to which extent I can increase the calcium silicate hydrate to have a mature concrete where capillarity pores, okay, are not percolated, and I will explain later where you have the minimum of this capillarity pores. Therefore, you need to have a glue, but a good quality glue. Okay, therefore, in this cement, okay, you have two reactions. You have two reactions. That is why if you test, let's say, blended hydraulic cement, if you test them after 28 days, if you go to 56, 91 days, you go to 6 months, you want to 1 year, we have a lot of data we can share with you. You see that the strength is just keeping going and going. You develop a concrete at 40 megapascal, you end up after 1 year, you have 80 megapascal. Therefore, the additional strength, indeed, you don't need it, but you need it to self-heal, to secure your concrete bridge or your concrete road or your balcony or whatever you build for durability regarding this exposure condition, especially when you have reinforcement. It's okay. Now, when I come to the SLS 1697, okay, now here you see we have a multiple mineral addition. It's not 2, we can have 3, we can have as much as we have on the table. Now here you have clinker, therefore again you have the same reaction with the two products, give you strength and weakness. Okay, therefore, of course, we have one constituent, for example, could be slag, another constituent could be fly ash. This has, as I said, is this aluminosilicate, therefore you have the SiO2. Okay, therefore this SiO2 will combine with the calcium, again from pozzolanic reaction, you get more strength and you mitigate the weakness. But it's not finished, because you remember what I told you. If I look OPC, I look Portland limestone cement, I look blended hydraulic cement, The second constituent, for example, in Portland limestone cement, I can put slag or fly ash, but it's minor, is less than 5%. If I go to blended hydraulic cement, like if I have fly ash cement, I can put limestone, or I can put fly ash, but this is minor, it's below 5%. They are not main constituents. But in the blended in the Portland composite cement, they become main constituents. Therefore, if I add high-grade calcium carbonate to the slag, or I add fly ash to the limestone, to the high-grade calcium carbonate, I have a third reaction that will take place. Because, you know, I said aluminosilicate. The silicate is forming with the Portlandite this pozzolanic reaction. But what to do with the aluminate? As, for example, if I put high-grade calcium carbonate, I can dissolve calcium. The calcium will combine the aluminate that is in the slag or in the fly ash that we did not use to form what we call another reaction, that is the nucleation reaction, that will form the MCAH, that is what we call monocarboaluminate. That is giving you more strength. This is the additional strength. That is why, even though you are reducing your clinker factor, you are producing more or equivalent high quality of hydrated product or glue. Okay, that make a big difference. And in this case, when we look, we have now three reactions. This is a triple reaction. Therefore, you see, therefore, we are fully taking advantage when I took to calcium silicate hydrate plus activation system, pH play a big role. We are able to fully take advantage of this main constituent of the Portland composite cement. That is why if you look in terms of hydration, what we call the hydration mechanism, this is what we call the pore blocking, or what we say developing high strength. What is this pore blocking? Very often you have heard, you heard that, you know, we talk about capillary pores, we talk about percolated capillary pores. When you do, for example, a water permeability test, you ask yourself why the water can go through my concrete, because you have a connected porosity. Therefore, with a triple reaction, you increase, as I said, the calcium silicate hydrate that lead to higher strength and also to pore blocking. Why pore blocking? Because even though you have a certain porosity, they are not percolated. They are not anymore percolated. That is why a gas or a liquid cannot go through it, which reduce, as you see, the permeability and therefore the durability of the concrete. Therefore, if, for example, schematically, you see, if I take cement grain, you see you have in the hydration reaction, the first one, you have calcium silicate hydrate, that is the strength, that is good, but you have also porous calcium hydroxide, the Portlandite. This is soluble. Therefore, if I have a different cycle of wetting and drying, you can see a white staining on the surface of your concrete. This is exactly coming from this Portlandite. Now, if I mitigate this Portlandite, I add the silicate for aluminosilicate material in the Portland composite cement, I can densify it by forming more calcium silicate hydrate. And suddenly, thanks to the aluminosilicate constituent that you put in your Portland composite cement, you can further improve the durability of your concrete. And at the same time, I will show it later in the slide when we move from normal concrete to high performance concrete, we have what we call the transition zone. Okay, the transition, how the glue, the quality of the glue of the cement hydrated product with the coarse aggregate. That is also very important. This is what we call the wall effect. Okay, how I can increase the bond in the wall effect. Because if you take, for example, I will show you later, if you take normal concrete and you break a cube of normal concrete, you will see you will not break the coarse aggregate. It goes in the cement hydrated paste. Therefore, if you go to high performance concrete, if you go to better quality concrete, you need, okay, to develop this wall effect, you need to increase the bond. How you increase the bond is to take out the Portlandite or the calcium hydroxide and turn it to what we call calcium silicate hydrate. That is really important. That is why we have this what we call the physical effect, where you can improve highly, you know, the compressive strength by having this kind of reaction. Now, you see, in normal concrete, in this slide, what you see, in normal concrete, what is written here that you know very well, that the strength is governed by the Ferré law or the Abraham law, that is the water cement ratio. Okay, I'm not going to tell you that because you know very well that if I increase my water cement ratio, my strength will go down in normal concrete. Therefore, it's very important to keep in mind that we don't have problem very often with the aggregate. Because aggregate properties are not often considered, except, of course, requirement regarding cleanness and grading. Therefore, in normal concrete, if you look at the microstructure in a normal concrete, okay, you see that you have high porosity and heterogeneity of the matrix. You have oriented crystal of Portlandite on aggregate. You see how this Portlandite is oriented in the interface with the aggregate that give you the weakness, flexural strength, E modulus, compressive strength, fatigue. If you go to fatigue, different cycle of fatigue, okay, you can develop cracks, internal cracks, okay. And at the same time, you will see that this mortar strength very often is lower than the aggregate strength. But when we go to and when you break a cube, I mean, you see very often you don't break the aggregate. It grows through the cement hydrated paste. Now, when we come to high performance concrete high strength, this strength is not governed by the water cement ratio anymore. Okay, and here the limiting factor could be the aggregate, because to improve, you have to control the water cement ratio. You need to have a good aggregate. That is why, if you remember the last webinar on ultra high performance concrete, the way to do it is just the inclusion of coarse aggregate is omitted in the mixed design. We just take it out. That's the way you do it. Otherwise, if you want to develop concrete up to 100 megapascal, you need to consider the role of aggregate, because the compressive strength is no longer related only to the water cement ratio like in normal concrete. And there is one important factor is the transition zone, because as I said, between the paste and the aggregate. Therefore, if you can improve it, you improve the bond, what the wall effect. By improving the bond, you increase all the engineering properties. And when I say engineering properties, I'm not meaning only compressive strength. That is how we build bridges that last for 100 years, 120 years. That is how we can have tall building where the modulus of elasticity is almost close to the E modulus of aluminium to 40 gigapascal. This is possible if we look after the coarse aggregate. And here the cement hydrated paste with Portland composite cement will really improve, okay, with the triple reaction, the transition zone between the coarse aggregate and the hydrated mortar. Okay, that is important that we keep in mind here when it comes to durability. That is why there is a notion when it comes to when we talk about high performance concrete is the gel space ratio. What is the gel space ratio? It's a ratio between the volume of hydrated paste, okay, and the sum of the volume of hydrated paste and the volume of capillarity pores. If you do, for example, mercury porosity, okay, or soon we are going to get in our innovation to industry collaboration in Peliego, the gas permeability meter, the Sambiro, we are able, okay, to look after permeability to gas, not only to water. And now you will see that here that this ratio becomes very important, because more we produce hydrated product, less we have capillarity pore. Therefore, this ratio will increase. By increasing the ratio, we increase the compressive strength. That is really important. That is fundamental. And that is why I say that when you test, for example, blended hydraulic cement, or in the future Portland composite cement, okay, or Portland limestone cement, please don't stop at 28 days. Continue to test your concrete after 28 days, and you will see you have a good maturity, and this good maturity will profit to the durability of the concrete, not only to the compressive strength. Indeed, you don't need it. If you design a 30 megapascal and you get 55, why you need 55? Why you have to pay for it? If you pay for it, is to have extended service life. Yes, instead of building for 50 years. A bridge I can build for 100 years. You agree with me? Therefore, that become economically interesting. That is the reason why it's not a cost per cubic meter, but how much is the return of my investment. That become interesting. That is why high performance concrete, even though per ton, per cubic meter of concrete, they cost sometimes 15 to 20% more, but still they are used to build, I say bridges with service life above 100 years. If you take, for example, high strength concrete, and you go for tests like in compressive strength, here you see that the breaking happen, the failure happen through the coarse aggregate, and that is the main reason. If you come to I2I, we have a grinder. Therefore, in some tests for high strength, for example, where we use cylinder, we need to prepare the surface. We need to grind the surface to assure the parallelism and the perpendicularity. Otherwise, you have eccentricity when you test in compressive strength. That is the main reason that we have to adapt even the technique of testing. And this is because the aggregate, okay, could be in terms of strength low than the cement hydrated product. Now, if I come now to the deterioration process when it comes to concrete, okay, when we look at there are what we call the internal origin, and you have what we call the external origin and the internal origin. I will discuss for the time, that is limited to me, the external origin. In the external origin, top one is corrosion. If you see failure, if you see concrete collapsing, they are all due to corrosion, mainly chloride or carbonation, or it can be also a chemical attack, mainly sulfate, for example. Okay, in Nordic country, you have the frost, but this is not of concern for Sri Lanka. There is also internal origin that are very important today. More and more we are discussing about in Sri Lanka, for example, alkali aggregate reaction or delay ethylene for mass concreting. This demand a lot of attention, okay, as the potential destructive has a huge potential destructive. Therefore, I will mainly focus on the corrosion and the chemical attack. Again, here, if I look corrosion due to carbonation, for example, corrosion due to carbonation. If I take, for example, a microstructure of concrete, as I told you, you will have calcium silicate hydrate, and if you do not use Portland composite cement or aluminum silicate material like slag, fly ash, whatever you put in your blended hydraulic cement or your Portland limestone cement, you have plenty of Portlandite. This Portlandite will combine the soluble CO2 that come to your concrete and form calcite. This is what I say, this is leachable. This is soluble. Therefore, if this happens, don't clean it. Leave it. Aesthetically, it's not nice, but leave it. Because the problem of it is this is stabilizing the pH. It keeps your concrete microstructure at a pH level where it is basic. Where it's basic, therefore the reinforcement is protected. But if this is continuously happening because you have high soluble CO2, you have high carbonation, you have a certain porosity, it's not compressive strength, it's a porosity, suddenly your pH can drop. Because you have decalcification, you have more and more of this Portlandite coming out. As soon as your pH drop, you are more acidic, for your reinforcement get depassivated. If your reinforcement is depassivated, the reinforcement starts to grow and to grow up to more than 10 times its volume. I'm talking about the steel bar. That is why you see rust somehow on your concrete surface. That's what you call the spalling. If you see this, it means that already the corrosion took place. Okay, and that is carbonation. That has nothing to do with chloride. And this is the Portlandite that is combining with the pollution. Let's say candy. Okay, now in country where the relative humidity is high. Sri Lanka is one of them. Okay, the diffusion and the carbonation is high because the soluble CO2 is high. Therefore, you have more CO2 that can combine with this portlandite to form calcite. Okay, therefore, it is even this is not a problem when it is in the desert in the Sahara, or if you go to the desert of in Dubai, whatever, they don't have this problem. They have another problem, but not carbonation, corrosion due to carbonation. Now, but Sri Lanka, this is important. Now, there is also corrosion coming from chloride, marine environment. Okay, here again, if you have chloride, it combined with the calcium in the portlandite, you form calcium carbonate, calcium chloride. Already, if you don't master and you don't mitigate the chloride diffusion, okay, or ingress in your concrete, you form calcium chloride. Suddenly, you have a pitting battery happening in your reinforcement and corrosion starts. But the danger here is what? That you don't see the rust because the reinforcement is disappearing. It's just cutting in one place. It's not the whole steel bar that is corroded. It's a battery effect. That is why you don't use sulfate-resistant cement based on clinker for marine structure. Sometimes people get confused with this, but this you should not use it. Why? Because you need aluminate. If you have aluminate, what happens? The aluminate will combine the chloride to form calcium chloroaluminate. And this calcium chloroaluminate, the chloride binding capacity, and therefore it reduces the chloride density. Therefore, you stop the corrosion. That is why porosity is built with INSE extra, that is a limestone, fly ash-based cement. And if you just look to all countries where they have marine infrastructure, they go with Portland composite cement. That is one of the reasons. You protect your reinforcement. It's not, again, about compressive strength. Therefore, sulfate resistance is only for chemical attack due to ethylene formation. Okay? But you can use sulfate resistance, but based on aluminosilicate like INSE extra, that is sulfate resistant, but not OPC, but blended hydraulic cement. And soon you will see sulfate resistant Portland composite cement, because you have aluminate in that cement that will combine the chloride to form calcium chloroaluminate. We call this the Frizzle salt. Okay, scientifically that's what we call it. Therefore, that is one of the main reasons here. And now you see, for example, if you look the chloride ingress, if you take, for example, a SEM1 that is an OPC or a limestone cement, in terms of corrosion, when you have high corrosion designed for 100 years, they are similar. But as soon as you move to Portland composite cement, you see SEM2M, M mixed in composite cement or slag cement, up to 35% or above 35%, the SEM3A or SEM3B, this we don't have them in Sri Lanka yet. Okay, therefore you see how the chloride density go down. That is the beauty of this Portland composite cement. Therefore, you have less diffusion of the chloride. Okay, that is really why if you take a porosity project, they use this test method. They have put what we call the durability indicators on chloride penetrability. This is a test, ISTM test. Okay, and when you are below 2000 micron, 2000 coulomb, you are what we categorize low in terms of chloride ion penetrability. Project like, for example, the new Panama Canal with 100-year service life design, okay, where the requirement is 1000 coulomb, water cementation 0.4 with Portland composite cement. We also have this test, we have it in our I2I. We have also another test that is now used more and more in Europe. Okay, the specific resistivity, what we call, you measure the surface resistivity of your concrete. Therefore, what you look after the chloride ion penetrability. Very simple test. It's a Procex Swiss technology. Okay, we have it at I2I. And these tests will give you also a very good indication in terms of chloride ion penetrability test. It has been used for this project in Ile de la Réunion. It's a viaduct, okay, in the Indian Ocean. That 100-year service life design, 700 million euro. Precast, more than 95% were precast online. It's a slag base, as you see, the off-white color. Therefore, you see, it's not about composite again. Now, chemical attack, sulfate, the same. If I take the Portlandite and I have sulfate, suddenly I form secondary gypsum. And this secondary gypsum will combine, if you have aluminate, C3A, for example, in your clinker, you form what you call 3-sulfur aluminate. That is ethylene, is expensive. And that is why you have swelling, you have cracks. Okay, therefore, that is why if you look after sulfate resistance OPC cement, the C3A, according to the EN, you have three categories. Either you have 0 C3A or 3% C3A or 5% C3A. The ICM 150 is below 5%. This is what you call the type 5 cement. But when you move to Portland composite cement, you don't have any more this problem. Because you reduce the amount of clinker, you reduce the amount of C3A, suddenly this type of cement are also highly compatible for marine infrastructure. Okay, therefore, this is, for example, experience, a personal experience I have from Canada. When I was in Canada, we have developed there the legacy INSI, that is Holcim. We have developed what we call the high performance antibacterial concrete for pig farm. Okay, the problem here is this with this small pig, that the parasite that sit on the stable, okay, with time they contaminate the small pork. Suddenly they get sick, and the death rate can go up to 25%. And in terms of productivity, this is the big loss. Second, there is some market in Japan, for example, they are ready to pay more than 15% premium if the small animal is not treated with antibiotic. This is why we call this is a high performance antibacterial. The way we did it is we design with Portland composite cement where we have transformed the capillarity to mesopore. Therefore, we have moved when you do, for example, what we call the gas permeability. You look and you realize that your capillarity are below 100 nanometer. Above 100 nanometer, this has a big impact on the compressive strength. That is why you have to reduce your water cement ratio. And below 100 nanometer, this is the durability. Shrinkage, volumetric change, or percolated gas that can come to your, or aggressive element. That is why you need to go to more to micropore, the micropore. Okay, that just to give you here, you know, the indicators we were looking for is low porosity. Nothing to do with the compressive strength. Okay. Therefore, by using this Portland composite cement with a triple reaction, I explain you have really high strength at all ages. You have denser microstructure, low permeability, lower heat of hydration because the clinker factors get reduced. High resistance to sulfate, as we explained it, to chloride carbonation that prevent alkali aggregate reaction. And last but not least, the leaching. That is very important. Why I say leaching? For me, I'm more concerned with leaching for reinforced concrete. Not only for the carbonation, but the leaching for the reinforced concrete is what? I have a water reservoir. I have a certain porosity. I have a lot of Portlandite. If the water permeability is a little bit high, I can leach out the Portlandite. So what I'm doing, by leaching out the Portlandite, I reduce the pH. Therefore, I have what we call a decalcification. And if the pH now reach 9, the reinforcement is depassivated. But the problem is, if you continue to have leaching, the pH go below 7, suddenly your calcium silicate hydrate is not anymore stable. Therefore, you start to lose strength. That is why some water tower can collapse, some balcony can collapse, we think it is a corrosion of the reinforcement. No, it's not only the corrosion of the reinforcement, it's just because we went to very acidic pH. That even though your CSH, your calcium silicate hydrate that is responsible for the compressive strength by itself, get reduced. Okay, that is really a very important as an engineering property. Now, giving you some example of Portland composite cement at international level. You know, I have presented very often this slide just to show, for example, what is the European domestic delivery in cement, let's say 10 years back. You see in this graphic, more than 50% is Portland composite cement. Okay, on top of that, you have pozzolanic CEM4, you have also CEM3, these are blast furnace slag cement, where the slag is above 60%. What is remaining on the OPC is about 25%, but if you dig on it, is not indeed 25%. Because very often some ready-mix player in Europe, like in Sri Lanka, they get their own slag or their own flash and do the blended concrete. Therefore, they use OPC, but the concrete is not OPC concrete. What we did when we did a market discovery, we realized that less than 5% of OPC are remaining in Europe and mainly used today for high-end precast, especially for some of the tunneling project where demolding is after 4 hours. But the technology of this type of solution, where the cost per cubic meter of concrete can reach $300 to $350. This is niche. This is not general purpose, and this is not even something that can be considered because this is very niche. Therefore, if you look the construction industry today, they are out of OPC. They are out of OPC. Now, an example in Switzerland, for example, in Geneva, where this Portland composite cement, CEM2BM, VLL, V mean flash, and LL mean high-grade limestone, high-grade calcium carbonate. This could be the product we will produce, hopefully, in Portland soon. Okay. Therefore, it is used for self-compacting concrete for loss fall, and you see the off finish, high workability, high strength in a very harsh environment. Winter, you have also very hot summer, successfully implemented. Also, it is used for residential and office building. This is in Zug. Okay, again, it's a flash and limestone composite cement. And when you look the color here, just this is not the normal color of the concrete. A pigment has been used because I know in Sri Lanka very often people like darker. Okay, but darker, the color has nothing to do with the quality of the cement. I can have off-white, beautiful cement with high strength, high durability. Okay, therefore we can just put a little bit of iron oxide and turn the cement darker, but doesn't mean the quality has changed. Okay, the color is just the iron content, but this has nothing to do with the strength. Therefore, here architects, they use color to express a certain form of warm or cool somehow object. Okay. In Vietnam, CEM2BVL, again the same. It's a flash and limestone. It is used for the foundation of a power plant, and for high slump retention requirement, no surface crack, excellent workability, pumpability, and low heat of hydration. This is in Finland. I like to present this example where you see how composite cement was used. This is, for example, is a SLL, is a slag and limestone. That is the product we will produce in Ruhunu, in gold. Therefore, you see, it is used to cast a bridge deck where the outdoor temperature was around 30 degrees, is summer. If you go today in Europe, is even 2 weeks back in Switzerland, it was 35 degrees exactly. But at the same time, in winter, we use the icing salt to melt the snow in bridges to keep the traffic open. Therefore, you see, this type of cement could withstand this extreme climate condition that show clearly that in terms of porosity, in terms of durability, it fulfills the engineering properties or requirements for the design of this type of bridge. the beautiful Rio Antillo Bridge in Greece. And you see here, it's a SEM2BM, but it is a ternary. Three different additions. W means it's a calcareous fly ash, a natural pozzolan, and a limestone, WPL. Plus, they use SEM3A. This is slag base up to 65%. You see, this bridge is 120 years service life design. Is not built with the ancestor of this green cement that is OPT. Therefore, you see, that is what I want to say here, that we have proven technology. We have really a great experience for more than let's say 2-3 decades. Okay, where we have been using this type of cement successfully in Europe. This is why they are in the standard anyway. That is a last example where the system here used the composite cement is with slag and fly ash. This is a water treatment plant in France. Okay, it treats around 600,000 cubic meters a day. Therefore, 50,000 tons of composite cement has been used to build 12 basins, where the deep is a big swimming pool, 10 meter deep. Here, you know, the guarantee was 40 megapascal at 28 days and also enhanced resistance to chemical attack. This is acidic. When I say alchemic, this is acidic attack here. Therefore, that shows clearly that you see composite cement has been used for different applications. Just to end up, I would like to say that this is what I call the natural journey we are taking together with the innovation, the INSEE innovation to industry collaboration space. I mean, Professor Ranjit, he talked a lot about circular economy when it comes to sustainability. Probably he will talk about it, but this circular economy is the same when you have a circular mindset, going out of the linear mindset where everybody do his job. But when you come to circular, we put it together. Therefore, we can have what we call open collaboration. Open in the main of openness, pre-competitive. We can have a lot of projects with government, customer, competitor, with supplier, with architect, with academia. That is ongoing anyway on our pipeline of activity in I2I. Speed is very important. Speed, because we don't have to send every time our cement or our concrete to Singapore or to UK to show that we have a certain, we fulfill certain requirements. This can be done now in Sri Lanka. The speed is there. It's important. We cannot wait. And the connectivity. Why connectivity is that it is important. We do not build bridges virtually. You agree with me? Therefore, it is really important that we have some harbor where everybody with his boat can go wherever he wants. But whenever he needs inspiration, he needs innovation, he needs collaboration, he just come back to the harbor called I2I. Therefore, he can put his boat there and start to collaborate, get new idea, okay, get inspired, and turn some of his opportunity to good business somehow implementation. Therefore, that is really, when it comes to Portland composite cement, it's the same. This journey is a journey that really take into consideration all these aspects. Okay, and also when you look to this I2I collaboration space, we have what we call durability space, aggregate space, chemistry and aerology space. We have dozens of tests, and none of them will test the compressive strength of concrete. If you go to the durability spaces, all these tests, or chemistry, aerology, all these tests, or none of them will test the compressive strength, because compressive strength is one of the engineering property. And as you have seen, and I hope that I could share some of my personal experience, that how durability, okay, is not directly linked to compressive strength. Therefore, it's very important that some of those indicators are well somehow investigated. And of course, we have the strength testing and wet space, where when we talk about strength testing, we have non-destructive tests, we have different type of tests we do. Soon we will invest on testing the e-modulus of concrete, okay, and that really will add a new method of or a new engineering property, especially for tall building, where we can assess, we can develop, we can optimize cost of high performance concrete, high strength concrete with the best e-modules. Therefore, as a conclusion, I would say that when we look over the past 2 decades, most of international and national cement and concrete standards have introduced what I call the performance-based specification. You have seen our challenges. If you look again, I talk about the car industry, they are switching totally to electrical. If you look the way we build, okay, the operational footprint is going down because people use more and more systems, new functionality for walls. They have isolated houses, very well thermal isolated. They use, I say, non-fossil energy, renewable energy. Therefore, this part, okay, of the 25% will decrease, but still the embedded CO2 that is more than 11%, that is locked down when we build, need to be tackled. Therefore, that is why this performance-based specification has opened and let really the industry to push on the innovation button. Okay, to reduce CO2, to have also more flexibility to optimize a mixed design to fulfill severe exposure conditions. Because we just cannot afford to build bridges only for 50 years. You agree with me? I'm not talking about the tragedy that can happen if a building or a bridge collapse. I'm not talking even about that. Also, the new Portland composite cement, it's an important milestone for Sri Lanka because we are catching up with international standards. This is good. It will give us a significant CO2 reduction for better living of today and tomorrow. Therefore, we are also helping Sri Lanka as I say a stakeholder. We are helping Sri Lanka at least to fulfill this Paris Agreement. A higher value addition to Sri Lanka and utilizing its resources. It's a synergetical effect. If I take limestone alone, if I take fly ash alone, if I take pozzola or aluminum silicate, if I mix them with water, they stay water and sludge. They will never harden. Therefore, it's a synergetical effect that play a role here. Therefore, if we push the innovation button, we are able really to have high value added and be less dependent. And I can assure you that in our R&D pipeline, we have a very interesting initiative, okay, to really work on this solution. And last but not least, is also when we look to the commitment on sustainable solution that have moved all continents without exception toward composite cement with a share over 75%. If you look domestic delivery in most of the country today, you will see that the share of this type of cement is more than 75%. Thank you so much for your attention. I hope that I could cover the topic. I could somehow highlight the important part of this new SLS 1697 Portland composite cement. Thank you so much for your attention, and I'm looking forward for your good comment, your question, and also the panel member to also somehow share their opinion, and answer to the question that can come from the audience. Thank you again so much.
Thank you very much, Dr. Moza Balbaki, Head of Products and Solutions Portfolio in Cement. Today is the 12th webinar session. Thank you for conducting the 12th webinar session, I2I knowledge sharing webinar session, the 27th knowledge sharing session. So we have a very good and a well-reputed, recognized and knowledgeable panel for the panel discussion. In order to conduct the panel discussion, may I invite our very energetic personality of INSI Cement, Head of Marketing, Mrs. Gaini Pereira. Gaini, over to you to conduct the panel discussion of today's session.
Thank you, Dishan. So good afternoon to all of you. Before we actually start, let me introduce the panel of today. Professor Ranjit Disanayaka, Senior Professor in Civil Engineering, University of Peradeniya, Sri Lanka, and the Secretary of the State Ministry of Rural Roads and Other Infrastructure, Professor Ranjit Disanayaka.
Hello.
Hello, Professor. Dr. Tushar Priyadarshana, Senior Lecturer, Civil Engineering, Faculty of Engineering Technology, Open University, and also the Chairman of T Small Holding Development Authority. Dr. Priyadarshana, welcome. And of course, finally, Engineer Mangala De Silva, Director, Co-founder, Sinago Consultants Private Limited, Council Member, Sri Lankan Standard Institute. So welcome, Engineer De Silva, to our panel today. So let me actually start from Professor Ranjit Disanaika. So one of the main questions actually what we have, so we heard from Dr. Musa Balbaki today that, you know, the importance of green cement or Portland composite cement. So let me give you a little bit of a background for the question. The nature of the construction industry, including its operations and supply chain, makes it one of the major contributors of carbon emissions in the world. But we have seen in the industry evolving over the past few years, mostly since the Paris Agreement in 2015, becoming more conscious of our carbon footprint and the invisible impact our industry makes in the world. So it's about the Paris Agreement. So how has this Paris Agreement on climate change impacted and motivated sustainable construction practices in Sri Lanka?
Yeah, thank you. The very interesting questions. Basically, when we go to the Paris Agreement, it is about the reduction of the temperature increase and the climate change, then the greenhouse gases, emission of the greenhouse reduction. So that then when you go to construction industry, it is a big part of the emission is responsible by the construction industry. Particularly when you go to the cement manufacturing, we emission a lot of carbon dioxide and other gases. Nearly 5 to 7% of the total carbon dioxide emission is responsible by the cement manufacturing. Therefore, if you are going for a green cement, that basically we are going to reduce the carbon dioxide emission. That means we are going to keep the pledge on the Paris Agreement. Even the Paris Agreement, as I repeatedly told you, that it is about the temperature increase and the climate change and the greenhouse gas emission reduction. Therefore, when you go to the sustainable construction, it is to go, supporting the Paris Agreement. As a Sri Lanka, we have already signed the agreement, as well as particularly the cement industry. If you go for the greener cement, that is very much go with the Paris Agreement. Thank you.
Okay. Thank you, Professor Disanaika. Dr. Priyadarshana, first of all, I must congratulate you on the new post that you achieved today. So congratulations, Dr. Tushara. Before we start, superior blended cement have been around for a long time and used across the globe in developed countries. But as we know through experience, Sri Lanka takes longer to adjust to new products that are not traditional OPC, even when they are proven to be equally stronger and more sustainable. So today the consumer market is more open to blended cements because the benefits are being endorsed not only by the cement manufacturer, but other industry stakeholder groups that people trust, like engineers, contractors, and consultants. So what are the opportunities and challenges as an engineer, contractor, a builder, or a consultant when developing sustainable concrete buildings with green cement such as Portland composite cement?
So thank you, Gaini. So for wishing me. So today, even though it's a quite busy day, so This is one of the sessions that I really wanted to join. And cement
Thank you
is
so
in
much for taking time.
yeah, cement is in my, used to be in my blood. Now it started cement plus tea as well. So actually, when we consider the overall cement standard evaluation and the evolvement of the in the world, so I can remember, so in 10-15 years back, so everyone wanted to use OPC. Then when come with different type of blended cement, so then people start different discussions. But nowadays, now as an example, now we had OPC. Now then in the market there was limestone cement. So many discussion. Now it has been well established limestone cement in the market. Then fly ash blended cement came into industry. So I can remember when we introduced all these. At that time I was in Holcim. So introduced, people used to say that, so this is just ash from this coal, and which is not good for the cement. But now it is one of the most established type of cement in the country. If you take the country, most of the major structures are use fly ash blended cement. And when it comes to the composite cement, this is a timely requirement we really need for the country, because we cannot just build with ordinary Portland cement. We cannot just build with one other cement, because we need good flexibility as engineers, as concrete producers. We need to have better flexibility. So I have a very good classic example. If you take in the world, everywhere in the world, people started to use blended cement, not because of not only because of this are sustainable, but those give very good solution for the industry. As an example, if you want workability, so not only the sustainable, but if you want to have workability, probably with this material, especially like fly ash, you can get better workability. So as I mentioned, so I will give very good example is the Burj Khalifa. This is built in Dubai, world tallest building. If I give just one example, its foundation is used more than 60% of slag in the mix. So you can imagine, because once everyone built the world's tallest building in the Dubai, they could have just used OPZ or the one type of cement. But they have not gone for this, because they need durability and some other properties to have very sustainable thing. So for the column and other elements, they are used fly ash blended cement, fly ash in concrete, because they need workability and all others. Then they went not only fly ash, but plus with microsilica. So I think Dr. Musa had done a very good presentation. But if I very briefly summarize for the audience, what we had at the past is ordinary Portland cement, just clinker plus 5% of some other mineral component plus gypsum. We used to say that clinker plus gypsum. Then limestone cement, we had clinker plus 15 to 20% limestone. Then blended hydraulic cement, we had clinker plus up to 35% of fly ash. But or it can be fly ash or pozzolana or slag. But we could not produce any cement with the mix of these, maybe with slag and fly ash. So to overcome these things, this problem and give better solution, I think this is composite cement will be one of the best solution for the country like us, which has sea around us. So we need better durability properties in concrete. And I was very fortunate to be in the working committee of this. When I was at the beginning, I can remember what are the discussions we had, and very good constructive argument. So I am very happy that we are ended up with this type of cement. But I think for the old audience also, I should remind that still in Sri Lanka, we have only, with this standard, we have 5 types of cement only, and no one produces masonry cement. So we have only 3 types at the moment. And with this, there will be only 4 types. But some other countries like Europe, they have 27 plus types in the market. So I think in the future, we need more and more type of cement. I think our users, our contractors, engineers, we should be very, very optimistic on this, and they should start to use this new material in construction to get sustainability in it. I think I took a little longer time because, as I mentioned, so concrete is in my heart. So thank you very much, guys.
Thank you, Dr. Theodashana. So, Engineer De Silva, let me ask you this question from you. Aside from the green cements contributing to global Paris Agreement targets in terms of reduced carbon emissions, the construction industry has been looking at more holistic ways to address our responsibility towards creating more awareness to sustainability construction practices. Not only focusing on environmental aspects of it, but also economic and social aspects as well. So in this context, how do green cements with low carbon footprint, such as PCC, what we've discussed, can contribute to extend the service life of concrete structures? I'm sure this question is quite interesting to listen to.
Yes, Danny. I would say, yeah, I mean, if you use this type of composite cement, definitely, I mean, it will be, that type of concrete will be in more equilibrium in acidic environment. So definitely the requirement for the, I mean, the concrete repair work, or else if I say in other words, the possibilities to degradation, I mean, degradation of concrete will be lower. So I think anyone who was listening to this Professor Musa's presentation, it was very clear that he was talking about this core diameter, which is less than 100 nanometers. It will be I mean, it's very good in serviceability wise, and also this type of composite cement, if you use for the concrete, it will gain the strength over the time. So it will be a little bit economical, some more economical, as well as I know we know this. I mean, some of the high-rise buildings and whatever structures we can see that some abnormal crack patterns are appearing due to so many fatigue cycles. So this type of cement is very good for self-healing. We all know this. I mean, all engineers know what is self-healing. For the self-healing process, this concrete is where this type of cement is very good. And also this, you know, this due to the less intervention, we have a low cost. It will be the cost for the during the service life, it will be very low. So I think my explanation will be enough, right? Okay.
Yes, Engineer De Silva. So, Dr. Balbake, I have one question from the audience. So the audience, one of Mr. Nimal Ranasinghe has asked us, what is the recommended curing period for PCC concrete to ensure completion of slow hydration reaction between supplementary cementitious material and calcium hydroxide?
Yes, I mean, when it comes to the, I say the hydration reaction, when it comes to Portland composite cement, okay, I mean, from a theoretical point of view, to fully hydrate cement, you need to use about 30% of its mass. Therefore, as soon as we have a water cement ratio around 0.35, 0.4, okay, the concrete starts its maturity, but the pores, internal pores, capillarity pores, gel pores are saturated. This is plenty of reservoir of humidity to further develop the chemical reaction with time. Why I say to further develop the chemical reaction, as I said that, for example, the second and the third reaction will not take place if you don't have aluminosilicate materials. thanks to the aluminosilicate materials, we have further development of hydrated product. Therefore, this saturated capillarity pores, saturated gel pores will turn to non-connected. They are not going to be connected because you form more gel, you form more hydrated product. And that is why if you test Portland composite cement over time, you see a maturity that is just increasing and increasing. Therefore, in terms of when you come to curing, of course, you cure concrete until the day of testing. If I have to test the concrete at 7 days or 28 days or 56 days or 90 days, I keep the concrete under 100% moisture condition to the time of testing. Okay, this is for lab testing to somehow compare apple and apple. Okay, but in reality, we have no really small cube of concrete. We have column, we have slab, we have a big element of concrete. The concrete stay always is a certain moisture. That is why in winter, I say condition like in country where they have winter, they have a problem with frost because the pore capillarity are always filled with a certain moisture, certain volume of water. Because the concrete to be fully hydrated, you don't need more than 30% of its mass. Therefore, if this water turns to ice, you form crystal ice, and this is going to grow and increase by 9% of the volume, you form cracks. You see, therefore, that is just to keep in mind that the beauty of this Portland composite cement that because the hydration of the clinker form lime, this lime will be used later with the silicate from the aluminosilicate material to form more calcium silicate hydrate. And that is why you have what engineer Magala said, that you have the self-healing effect with time. That is very interesting because even though some small micro cracks that develop at early age are closed later because you have just sealed with a more hydrated product you have formed. I hope I have answered to the question.
Yes, Dr. Balbaki. Let me actually go back to Professor Dissanayake. Professor Dissanayake, so this is as a chairman of the Green Building Council of Sri Lanka, right? So this is regarding our strategy or the way forward for Sri Lanka when it comes to. So green building strategy, how Sri Lanka is positioned compared to the other countries in the region. Could you tell us the opportunities and challenges for sustainable construction that we have currently, or we would have in time to come?
When you come to the Green Building Council of Sri Lanka, we are a member of the World Green Building Council. So in the region, we are one of the active member in the greener building practices. But I think India is doing much better than us. But next to India, we are doing pretty much of work for the time being. The aim of the vision of the Green Building Council is to transform the Sri Lankan construction industry with the greener building practices. I think we in order to do that, we have several strategies lined up. For example, we have the certification tool for the building, and of course the material and the institute, infrastructure, and various way we have developed the several tools in order to tackle this one. And particularly when you go to the cement, we have a material labeling system. So that I am pleased to say that for the time being, we have certified the INSI cement as a green cement. So that likewise, we try to find out certify the material which are more greener than conventional material. So I think as a country, we are with the work that we are doing through the Green Building Council, we are trying to convert the Sri Lankan construction industry to greener practices. I'm as a chairman of the Green Building Council, I'm so happy that the help that we are getting from the industry is very much satisfactory level. I think there are a lot to do more, and We have been training a lot of professionals, but now they are working in the industry. Then through that, we are mobilizing our action plan to the construction industry. That's it.
Thank you, Professor Disanayake. Dr. Priyadarshana, you spoke about Burj Khalifa before. This is also regarding something similar, a question. How can a combination of different supplementary cementous materials such as flax, fly ash, high-grade limestone or silica film be beneficial for the design of high strength, high performance and sustainable concrete?
Okay, Gaini, this is a good question. So as I previously mentioned, there are some, I think for the audience, there are some thumb rule. When you use, say, fly ash, if you want durability, you have to use at least 25%. And if you want strength, like 15 to 20% would be the grade. And if you use slag for durability, you have to use at least 50%. And for the strength, probably lower amount can be used, can be 20 or plus. Microsilica, when you use, you should not go beyond 10%. So likewise, there are some thumb rules. These can be used as you wish and based on those properties. So as an example, so as previously mentioned in Burj Khalifa, for the foundation, they have used slag because those are very big foundations. So you can easily pour it and do it. But when you want workability kind of thing, it's better to go with fly ash. But say as an example in high-rise building, if you want to design columns with 70 MPa grade, so you need both workability plus strength. Of course, if it is a major structure like Lotus Tower, you need always durability, which means sustainability and all others as well. So in that case, how do you manage all these? Based on your strength requirement and durability requirement, then you can use, say, fly ash like 10-15%. Then you can achieve the particular strength. If you feel that you need more strength, then probably you can add microsilica kind of materials up to 10%. So likewise, we can adjust all these material in a way that I think even INSEE has facilities to do that, and there are pre-mixed design. Likewise, then we can blend all this together and we can achieve whatever strength or durability or the sustainability as you wish. I hope I have answered the question.
Yes, Dr. Priyadarshana. This is also actually going back to engineer Margareti Silva. Also something similar. So we spoke about structures now. What would be the contribution of such a green cement on improving some structural engineering design parameters such as E-modulus, shrinkage, creep, and axial shortening in high-rise buildings?
Okay, Gani, it will be a very, very technical question, right? Maybe I'm
Definitely.
that will be a, I mean, that may be interesting for these young designers, those who are doing structural analysis. I mean, when we all know this, when we are using ordinary Portland cement and using concrete with ordinary Portland cement, when we are doing the structural analysis, most of the time we had the habit of not changing our parameters in compute analysis. For example, creep coefficients or the Young's modulus and whatever the parameters applicable to the axial shortening and other things. I mean, we don't have much room to play. That means we don't have much. We can't do much variations. But in this, with the introduction of this new composite cement, then the structural engineers has more freedom to do their designs in more efficient way. I would say, of course, I can remember about 18 years ago, this University of Moratuwa, I don't know whether Professor Jayasin is with us or not. I can remember 18 years ago, he did some research works in axial shortening. But now, I mean, after 18 years, there are a lot of structures, a lot of high-rise structures are coming here. So the axial shortening will be very critical. I'm sure, I mean, with the introduction of this composite cement, we can have more effective designs, and also that is the very reason actually. I mean, we have Dr. Tushar was talking about this Burj Khalifa and also the Petronas Towers, or else the Scotia Plaza Tower. Whatever the thing, that is the very reason for them to go for composite cement, right? So I'm sure these designers can now enjoy with their designs with more flexibility, and they may have the chance to change some parameters, and they can produce a good design. For ultimately, it will be better. I mean, it will be good for the industry. I hope I answered your question.
Yes, you did. Definitely, it will be. So, looking at the time, I have one question to ask from Mr. Jan Koenig, Executive Vice President, Sales, Marketing, and Innovations at TNC Cement. He's also in the panel at the moment. Jan, just to want to discuss, one of our audience has asked us about the cost and the price comparisons when it comes to PCC and OPC. So would you be able to let us, answer this question for us, how we can mitigate this, or what kind of solutions and what we can offer?
Well, I think price is always a good question. And on the other hand of price, something what we pay for comes value. And what we can see, what happens currently around the world, for example, freight rates, and Sri Lanka still needs to import many raw materials. Freight rates, they have tripled since January. And many products are getting more expensive and more expensive. And in the end, for sure, we need to mitigate it. By using as much as we have locally, we can mitigate to pass on certain cost increases which we were otherwise imposed. But I think much more important is that the new Portland composite cement gives a significant more value to the consumers or to the house builder or high-rise builder. Overall, the structure, the design, what Dr. Tushar also mentioned, could be changed. The parameters can change, what Engineer De Silva mentioned. And with that, you can design exactly based on your personal performance criteria, whether you want to have a house which lasts 30 years or a house which lasts 120 years, a specific design with the minimum resource input which is required. And that's a big benefit. So compared to using an OPC, if you don't change the design, it will simply last much longer. And that is already a huge value. Otherwise, you can change the design and make it slimmer, and it will be as durable as before. So on the one hand side, we can mitigate to pass on cost increases which are happening around the world. You've seen with the freight rates as one example. Oil increased from $25, $28. It's now above $70. And in the end, we can really mitigate it if we use our Sri Lankan resources optimally. And I can say that composite cement has now recently been also established in Bangladesh, just recently in Cambodia as well. So it's the clear trend towards that. And I'm very thankful to all the panelists here, but also our activities with all the academia, the working community, etc., that we have made this milestone, this step, which will definitely be here for the next 30, 40 years. Big milestone.
Thank you, Mr. Koenig. Before we actually end, let me ask the last question from Dr. Balbaki. This is straight coming from his presentation itself. Could you please illustrate or maybe give a brief understanding of the triple reaction in a more simplified or straight manner for our audience to understand?
Your question is to simplify The triple reaction.
Triple reaction?
I mean, to simplify it, because I saw something, somebody was asking somehow about water, I say, water protection, you know. This triple reaction is just based on physico-chemical reaction, depending on the nature of the constituent of the cement. Therefore, when you have OPC, you have one reaction. When you have a blended hydraulic or Portland limestone cement, you have two reactions. And when you have Portland composite cement, you have three reactions. Now, this three reaction, okay, if you take the first one, we develop a good product called calcium silicate hydrate, but the problem is the Portlandite. Therefore, when you come with the second reaction, this Portlandite is transformed to calcium silicate hydrate is good. And when it comes to the third reaction, because I have discussed about the minor addition. Now, if you take limestone or flash or slag in the Portland composite cement, they are not anymore minor. They are main constituent. Therefore, you have a third reaction where you combine now the calcium and the aluminate to form this monocarboaluminate. Therefore, you have addition of a good quality glue, let's put it like that, addition of good quality glue that make your concrete become more, let's say, impermeable. And that is why when you look to chloride diffusion, when you look to gas diffusion, when you look to water penetration, the value goes very well, very down, because this good quality of let's say of glue, you know, make that this porosity is not only reduced, but it is not connected anymore. It's not percolated. That is why, as I show in some of the example, how the chloride diffusivity really got almost half when you move from, let's say, one reaction product OPC to a three reaction product like Portland composite cement. That is really, if I can make it more simple.
Thank you, Dr. Balbaki. So I hope our attendees would have actually would have understood more on this aspect. I know that in the presentation also you went into more details. So that concludes our panel discussion for today. Thank you so much, Engineer Malagala Silva, Dr. Tushara Priyadarshana, as well as Professor Ranjit Dissanayake for taking part, and of course, Dr. Musa Balbaki and Jan Hunik today. So let me give back to Dishan to take over from me. Thank you.
Thank you very much, Gaini. Gaini is our head of marketing for INSI Cement. Thank you very much for conducting very useful and productful session with Dr. Moza Balbaki, Professor Ranjit Dissanayake, Dr. Tushara Priyadarshana, and Engineer Mangal Silva. So may I invite our General Manager, INSI Concrete and Industrial Sales, Engineer Nandanamula Tudua, to give the vote of thanks for the 12th webinar session organized by INSI Eye-to-Eye Collaboration Space. Engineer Nandanamula Tudua, over to you.
Thank you, Dishan. First of all, let me thank Dr. Musa Balbaki, our head of products and solution portfolio in Cement, for the wonderful presentation, elaborating all what we get as Sri Lankans with these new standards. And special thanks to our panelist, Professor Ranjit Dissanayake. Thank you very much, sir. And Dr. Tushara Priyadarshana. Thank you very much, Dr. Tushara, and Engineer Mangal Silva. Thank you very much for participating with the busy schedules. So most importantly, big thanks to all the participants who joined this session. This is our continuous 12th webinar session which we have conducted in Eye-to-Eye. So we hope at least by next month we can have a physical event at Eye-to-Eye. And our team thank you very much. Our Jan Koenig, our Executive Vice President, and the commercial team and the I2I team behind behind organizing this webinar event. Thank you very much, and hoping to see you all at our next webinar session. Thank you.
Thank you, everyone.
Thank you, everyone. Thank you very much, and see you all with the 13th webinar session of INSEE I2I collaboration space and the 28th knowledge sharing sessions in next month. Thank you very much and have a good day.
Thank you, everyone. Thank you. Bye-bye. Bye-bye.